Okay, so I don't know exactly what happened, but the Maple sort of locked down completely, and I recorded some video where I was swearing a little bit. So I think in order to, uh, in the service of academic decorum, I have removed this part of the video, and I will start over. So I simply, so in the part of the video that you don't see, after some swearing, I stopped Maple, I reloaded it, and I recomputed the numbers. And now, for some reason that I don't really understand, this now works, or rather, I don't understand why it didn't work before. So essentially, what I've done here is I've asked Maple to look at these numbers and see if it could recognize them after helping Maple by dividing by the appropriate power of pi, so that what I have here should be rational. And so this turns out not to be necessary anymore, but the kind of thing that I would do in order to speed this up is that you can actually tell Identify to look only for a rational. So there's some flags that you can put on. So all false, rational, true means that I disable all the searches for other values except for finding a rational. And this works. I mean, this would speed up the thing, but this now works impeccably without it, so I don't need it anymore. So actually, in the earlier cases that I looked at, you can see that, of course, there is an error here. Right? This number that I'm looking for, the number that I'm trying to recognize, is this number here, and it's clearly a rational, which you can see by the fact that it has a periodic decimal expansion. And of course, the values down here are wrong. Like they are results of round-off errors. And so what I could actually do when I was struggling with Maple, I could force it to find the right value by removing these imprecisions at the end and just feeding it the first part. But this now works, so who knows? So I mean, this of course is unfortunate, but it's quite common that when you work with Maple this way and you have to have high precision and long computations, Maple becomes slightly erratic and behaves in ways that somehow is different from time to time. And this is very unfortunate when I'm trying to record it, of course. But it's almost equally unfortunate when you're trying to do something that you can reproduce and you want to show other people. So actually, remember when I said up here that I didn't quite believe this? Well, I guess maybe I'm going to have to believe it now, because with the high level of precision, I still get this very uh, small fraction, which is just a third of some number. So we're clearly getting something which is not just random noise. This is meaningful, and I want to see if I can understand what's going on. So we're back now into the realm of analysis of integers, because I have fractions, right? And of course, a fraction comes with two integers, and it's usually not a very good idea to try to understand them separately, because there will be some cancellation going on between them. But I'm simply going to factorize the fractions that I found and see what kind of patterns emerge. And the first thing that looks interesting here is that I have some numbers in the denominator that look quite small. And so, I mean, when I factor them out. So these numbers, of course, are not very big to begin with, but they also have the property of being products of fairly small primes. So in order to get rid of the fraction, I'm just going to multiply it by some power, some factorial. And after a little bit of trial and error, I found that I had to do 2 times I plus 1 factorial. So of course these are the even values. So this is 2, 4, 6, and so on. So I have that, but it turns out not to be enough, right? If I do it like this, I'm 1 prime short. So I put plus 1, and now I get numbers that are all um, integers. And of course, now that I have numbers that are all integers, what could be more tempting than to feed this to the online encyclopedia of integer sequences So let me do that. But the thing is that I don't get anything out, right? So of course I could now go in and tell the online encyclopedia of this integer sequence of how I made this sequence. But instead I'm going to go back and see if I can get a little bit further in understanding what's going on here. And now looking at the numerators, there is actually something interesting going on, in the sense that, as opposed to the case in the denominators where I got very small primes, here I actually get very big primes. Right? So I mean, it's somehow interesting that this number here, which is not super big, has a huge prime like this one in its factorization. It's prime factorization. So one thing that you can do with these big primes is that you can essentially, you could try to Google them, but and I think that would work, but you can also put a single entry into the online encyclopedia. And so what you get here is something that we've talked about before, the Mersenne numbers. So the Mersenne primes are the numbers of the form 2 to the n minus 1 that happen to be primes. And what Maple has here is the list of all these numbers 2 to the n minus 1. And having gotten this hint, going back and looking at what we have here, there's a lot of Mersenne primes, right? There's 2 to the 3 minus 1. There's 2 to the 5 minus 1. There's 2 to the 7 minus 1. And we find several of these. This is also a Mersenne prime. This is a power of 2 minus 1. So, I mean, it's sort of striking that these numbers occur. So now that we see that they occur, we can try to get rid of them, right? So what happens is, suppose, again, this is a bit of trial and error. I do 2 to the 2 times I minus 1 minus 1, and I get some numbers out. They're not all primes, but they all occur in these values here, right? So the last value, which is the one that made me notice, is I have that here. The second one is also prime from the end. That's also prime. Then this number here is not a prime, but it's a product of some of these numbers here. This one here is a prime. I find it here, and so on. So what's going on here is that we have these factors in the values that we're looking at. So if I take these big numbers here and I try to tame them a little bit by factorizing them like that, I get this number out like so. Right. So what happened here, of course, is that I mean I needed a little bit of help here, because the number 2 to the n minus 1 are not all primes, so they don't occur in the list of primes. But since the whole idea of looking at Mersenne numbers is that there's a high probability that these become primes, then the information is somehow preserved even after I do the factorization. So this is what works. Okay, so now I've tamed this a little bit by dividing through by this number that I know always, well, I don't know if I know it, but I mean, I've seen that it always divides. So I try to plug this into the online encyclopedia. Again, no hit. And then after scratching your head a little bit, what you can see is that these numbers are all even. And so you might think perhaps that you divided by a number which is a bit too small. So what you can try to do is you can cancel out these 2's. So these are now, I just divided by 2. And I plug this into the online encyclopedia. And then I do get a hit. And the hit I get has something to do with Bernoulli numbers. There's also this 2n plus 1 factorial that I actually put in myself. So, I mean, I put that in myself in order to cancel the denominators in these fractions that were difficult for me to deal with. And in fact, this thing is more or less the same. It's the Bernoulli numbers that are also fractions. They have been canceled out in roughly the same way as what I did, which is fortunate, because then I can recognize the Bernoulli numbers. So I don't think I will do that here, but the point now is that now I can go back and I can say, okay, this number here, which was the fraction transformed a little bit is the Bernoulli numbers transformed a little bit. And then you solve the equations and you clean things up, and you get a very nice expression for these numbers being essentially pi to the relevant power, the same Bernoulli number, and then something of the form 2 to the n minus 2. So you can get a very nice expression for these numbers that Maple were not able to compute, and you do this for all n. So what is it that we have done? And actually, because the Bernoulli numbers also tend to be 0 at odd values, you actually can get something that works for all n, not just the odd, not just the even ones this way. Of course, this is not a proof, but then when you study the theory of the Bernoulli numbers that now we know are relevant, there's a relation to actually to the zeta function that you can use in order to do a proof of this fact. Before I end, let me point out something which is actually very common in this kind of work. I was really interested in this thing here, right? And I now know that this is pi square. I mean, I could have made a complete proof that this is pi square over 3. But I was led to this insight and the relation to the Bernoulli numbers by looking at other powers. So I was, in a sense, branching out from the original question to a more general question. And this, of course, is a way that mathematicians tend to work quite a lot. I mean, instead of looking at one value or two values, you generalize it into something that perhaps, I mean, in principle, this is harder because it's a more general question. But sometimes a general question is easier to answer because you can see more structure by looking at the general question. And this is exactly, I would claim, what happens here, because I look at 10 of these values. I get enough information out that I can get a sequence that I can then feed to the online encyclopedia of integer sequences. Of course, I couldn't do that with the small numbers that occur in the beginning of this sequence here, but like these 2 or 3 numbers here, that's not enough information. But using the generalized question, I can generate more data and put that into the various inversion tools. This is a very common way of working, and you should keep alert for opportunities for doing this. Even if you're working with something more specific, it's sometimes a very good idea to generalize a question before you throw this machinery at it.